Hello and welcome to the homework help video for the semester 2 final review. I am most likely going to do this in parts because my computer does not handle long videos very well. Not sure how many parts at the moment. We'll see. Let's go straight into number 1 here, and we want to find the domain and range of this shape. The domain is the smallest to the biggest x value, and if you follow the shape, you can find any x value. For instance, this right here, this is what, 3? And yep, it looks like about 3 comma 2 is a point. Maybe it's exactly 3, 2, maybe it's not. So the smallest x value we can find is going to be the point that's furthest to the left, and that's this point. The biggest x value is going to be the point that's furthest to the right, and that's this point right here. And those x values are -4 and +8. Hence, -4 to 8 is our domain. Notice I'm using the less than or equal to signs because they're points that you can actually point to, and they really do have x values. It's like, yeah, this is 0.8 comma, what is that, 5 or so? And likewise with the range, the only thing you got to watch out for, particularly with the range, a lot of times it's not an endpoint that's your lowest point. So this is the lowest point, not this endpoint here. And this point has a y value of -6. On the top side, yes, we do have an actual point. Looks like it's actually drawn slightly above 7. I think they're probably just trying to go for 7. That's one of the problems with graphs. You have to be very, very precise. Otherwise, like, am I supposed to interpret that as a little bit above 7? But whatever, I'm just going to say -6 to 7. That's most likely what they were going for when they were writing this question. And there's our range. Number 2, we are finding the roots. So this is unit 2. We're using the quadratic formula, so I plug in. And nothing too spectacular here. Just make sure you're plugging in correctly. Make sure you're getting, signs correct. And we should have 6 plus or minus the square root of -20 all over 4. One of the two key steps is here where we would say, all right, well, -20, that's -1 times 4 times 5. And we choose 4 because 4 is a perfect square. Like I could have chosen 10 times 2. That's also 20, but neither of those are perfect squares. So I am looking for that perfect square in there. And then cool, square root of -1, that's I. The square root of 4, that's 2. And the square root of 5 is just the square root of 5. This is the other key step. If you leave it like this, you actually would be marked down a little bit. And that's because you can actually factor out a 2 from the 6 and the 2 here. We can factor that out. You can imagine this 2 sitting outside some parentheses. It'd be like 2 times 3 plus or minus root 5i. I don't know if you can imagine that. I can. And then, so we have a 2 times this junk here, and then we have a 2 times a 2. That's 4, right? So we cancel 2's in the numerator and the denominator, and that's how we end up with our answer. 3 plus or minus root 5i all over 2. Okay, moving on, number 3. We are doing polynomial long division. And yeah, if you remember it, it's fairly simple. I have a few little quirks. But you're just looking at that leading term, 4x squared divided by x. Well, that's 4x. You multiply back just like normal long division. 4x times x is 4x squared. 4x times 3 is positive 12x. But be careful. I'm not adding 5x and 12x. I am subtracting. You subtract in the process of division. So we subtract 5 by 12, and we get -7. Once again, leading terms. -7x divided by x is -7. Multiply back, yada yada. It's not -2 minus 21, it's -2 minus -21, which makes it -2 plus 21, which is how I get my 19 here. And then, just like regular division, you put the remainder above the thing you're dividing by. So if this was like dividing by 3, then it would be 1/3, but now I'm dividing by x plus 3, so it's 19 over x plus 3, So that's our answer. Number 4, we need to know the shape, like what function is that indicative of. This is an absolute value graph, 100%, because it's a V. Sure, it's upside down, but it's basically linear, only broken up into 2 different halves. And that makes it absolute value. So all we need to know is h and k, which is told to us by the vertex. So -2 and 6. We need to know that h is still backwards when you plug it in. It's so therefore it's going to be x plus 2 in the absolute value and plus 6 at the end. And the a value, just like most a values, we get it from how do we get to our first reference point to our second reference point. We have to go down 3 times, therefore a is -3. Bam. I would expect you to know that that would work the same way if this is a quadratic. That would work the same way if this was a square root. It would be the exact same a, h, and k values, no matter the function, right? So moving on, number 5. What are the transformations that yield these this function below? And again, the parent function is x squared. It has an a value, and that's a -2, a negative a value. You may remember it says it reflects. That's a word we haven't really used that much in a while, but it's a thing. And because it's a 2, and 2 is a number that's bigger than 1, we say it stretches vertically. We have an h value here that shifts it left because h is opposite. He's the liar. K, he's cool. We shift up. And that's it. You could mention how many units, but just naming the transformations will be fine. Factoring this one, we could just use that this is the rules of difference of squares. In fact, that's how I actually solved this one now that I think about it. And a difference of squares, oh, sorry, I'm getting ahead of myself. How did I know that it was difference of squares? I mean, 11 times 11 is 121. X times x is x squared. Y squared times y squared, that's y to the 4th. So these are all things that you can multiply by themselves, and that's what I show here to get the first thing. And then the second term, let's use a fancier word, is just 7 times 7. So I have all the values that I can multiply by themselves, I can square in order to get the first term. Again, same deal with the second term. That one's easier. It's just 7 times 7. That makes it a difference of squares. And the rules for difference of squares, very simple. It just says you take here these things, these values that you're squaring in order to get what you actually have here. Yeah, just put them all in that in 2 sets of parentheses. And so it's 11x y squared. That's the first term. And then 7, that's the second term. One of them is going to be plus, one of them is going to be minus. Doesn't matter which one's which. So if you said minus first and then plus, I would totally accept that. No difference at all. So there you go. There's how to factor that one. The other way to factor this would use the box method. You'd put this in the top left corner, this one in the bottom right corner because it's a constant. Be like, all right, what can I multiply to get these values? You'd get the same thing, and then the other 2 boxes in the box method, the bottom left and the top right, would you would have a positive and a negative of the same thing. Try it for yourself if you don't believe me, and they would cancel out. That's why there's only 2 terms in this and not 3 in our, like we see in our normal things that we're trying to factor. Okay, I'm going to go ahead and move on to the next page. All right, here we are in number 7, and on this problem we are supposed to divide these rational expressions. Yeah, sure, no big deal. And in order to do so, we have to know, well, to divide any fractions, no matter how ugly they look, we need to copy dot flip. We don't need matching denominators, anything like that. So I end up copy dot flipping. I usually factor first, so that's what I did. X plus 2 times x plus 3, that's x squared plus 5x plus 6. Again, do the box method if you don't believe me. X plus 5 times x minus 4, that's the bottom left one, so on and so forth. You can see how I factored. So basically, I factored each of them. I canceled matching factors on the numerator and the denominator. So we see x plus 5 in the numerator and the denominator get canceled. X plus 2 as well. We ended up with 2 of these x plus 3's in the numerator and 2 of the x minus 4's in the denominator. And that's a common trick, especially in division problems. Watch out for that, where test writers, that would be me, would put 2 of the same thing. And in the original problem, you're like, oh, look, x minus 4 on the numerator and the denominator. I want to cancel that. But you need to copy dot flip first, turn it into a multiplication problem. Only once it's a multiplication can you actually cancel numerator and denominator. Then we get 2 of these x plus 3's and 2 of these x minus 4's on the same side. So that's x plus 3 squared over x plus 4 squared, x minus 4 squared. And we have some excluded values. X cannot be -2, X cannot be -5, X cannot be 4, and it also cannot be -3, and I'll point those out. Let's see. -5 because of X plus 5, +4 because of X minus 4, -2 because of X plus 2, and then -3 often overlooked because it's in the numerator, but on the original, it was in the denominator. We do have to include that one because even in the original, you can't have a 0 in the denominator. It's just not allowed. So that is a part of the excluded values. In fact, that's actually why this is written all squished at the very end, because I actually forgot about that one at first. So if the teacher can easily forget about it, you certainly can, so be careful. Number 8, simplify this thing. Yeah, sure, no big deal. Once again, I'm factoring. This here we have a common factor. Don't forget that that's still a thing that you can do. You are expected to know how to factor in multiple different ways. And I see x plus 2 on both the numerator and the denominator. Cross it out. My excluded values are -2 and 5. I do not need to include 0 because that is on the numerator and it was always on the numerator. And it's fine if the numerator is 0. I don't care. That just means the answer is 0. It's only when the numerator is on the denominator. Come on, man. It's only when the 0 is on the denominator that it's bad, because then you're dividing by 0, and that's not 0, that's undefined. So, careful. Watch out for that. Number 9, simplify. Easily the hardest problems from this unit. By the way, all of these problems were from Unit 5 that we're simplifying these complicated looking fractions. And again, the trick is to factor. It's always to factor, but on this one we're subtracting. You need matching denominators. This one had an x plus 2 and an x plus 3. This one had an x plus 2 and an x minus 2. So the left-hand denominator did not have the x minus 2, so I put it. I just multiplied both sides by x minus 2 over... Wait, what? Multiplied the numerator and the denominator by x minus 2. Words are hard. The right-hand fraction didn't have a factor of x plus 3, so I put it. And now that they have matching denominators, I can say, all right, well, 1 times x minus 2, that's x minus 2. 1 times x plus 3, that's x plus 3. I am subtracting here, so I do need to subtract this. X minus x cancels. -2 minus 3 is -5, and that's where I get my answer. Excluded values still apply. Number 10, simplify. This one's already multiplication. I'm not going to spend a lot of time on it. You factor, you cancel, you see what's still there. You could argue that this one actually could go a little bit further. You could say, oh, x divided by x is 1, and you have 1, not in a fraction or anything, 1 plus 4 over x. That would actually be another perfectly acceptable answer, but I'm totally fine just leaving it like this, all right? Excluded values, -3, -2, 1, -1, and 0, and there they are, -3 here, -2 here, -1 there, and 0 there. Number 11, we're supposed to find the inverse of the function. The concept of an inverse of a function, again, kind of asks, what steps do you have to do if you were going to plug in a number for y? For instance, if I was going to plug in 10 for y, what would I have to do in order to solve for x? Well, I would have to get rid of this plus 1. Then I would have to get rid of the exponent here, because you can't get to any of those things in the parentheses till you do. Then I would have to get rid of this minus 2. Then I would have to get rid of this 3. And that's exactly what I do. I get rid of the plus 1 first. Then I get rid of the power of 4 with a root of 4. Then I get rid of the minus 2 with a plus 2. And then I get rid of the 3 with a division by 3. That's the inverse function. So if you want to plug in something for y and solve for x, plug that same thing in for x here, and it'll spit out the answer will be here. That's what you should have plugged in for x in the original, right? So be expected to be asked about inverse functions, and not just how to do them, but like what do they mean? And it is just the set of operations that you have to do in order to solve the original equation if you were to plug in for y and solve for x. All right, moving on, number 12. I ran out of room a little bit, so I had to write some work on the left, some work on the right. It got a little messy. That's okay. So first, we're just multiplying this stuff together. This is all just exponent properties. And we multiply numbers times numbers and like variables times like variables. So 2 times 3 gets multiplied. And you can do that in isolation. You don't have to worry about the variables. You don't have to worry about the y's when you're multiplying the x's. X to the power of 3 times x to the power of negative 2. Well, that's x to the power of 3 plus negative 2, which is 3 minus 2, and that's the power of 1. And anything to the power of 1 is itself, so that's just x. Y to the power of 2 over 3. So this would technically be the cube root of y squared. And y to the power of 1/3, that's just the cube root of y. But written in exponential form like this, we can just do the same math that we just did, add the exponents because you're multiplying they're the same, two of the same base. 2/3 and 1/3 makes 3/3, aka 1, and y to the power of 1 is just y. So we ended up with 6x, y, and that's our answer. Number 13. Again, just transformations. This is what I was talking about. It doesn't matter what function this is. This is cube root. We didn't even study cube roots. It doesn't matter. We have an a value of 2/3. That's a vertical compression. This could have been square root. This could have been tangent. It doesn't matter. We have an h value of -4. So you know what? This thing shifts 4 to the right. And we have a k value of -1. This thing shifts down by 1. So it doesn't matter the function. I could throw secant at you. We didn't even really study secant that much, you know, and we could still list the transformations. Number 14, to find the inverse of this function. This one's much easier. It's fewer operations. So again, I forgot to mention the other one. We do switch x and y, and that's something that, you know, you're assumed to know, blah, blah, blah. We're going to cancel that square root by squaring. We're going to cancel this -1 with a +1. We're going to cancel that 3 with a division by 3. And there's our inverse function. It's just all the operations we see here, but opposite of them. Instead of square root, we see square. Instead of a -1, we see a +1. Instead of a times 3, we see a divided by 3. And other than that, order does matter. That's why we go through this process of solving in a particular way. Describe the key features, aka the reference points, of the graph of the function. Sure, I will say that key features, and on the final I will be specific, but key features do include other things such as where asymptotes are, and that's not the reference points, you know. So if it's a function that has asymptotes, I will make sure to specify that. But anyways, this is a square root graph, so it has all this stuff here, this -2 and this +1, sure. We have to know, okay, in the original, square root has reference points at 0, 0, and 1, 1, because the square root of 0 is 0, square root of 1 is 1. So since we're shifting to the right, left and right, that's x. And so that 0 is going to shift right 2. Well, right just means more. What's 2 more than 0? It's 2. What's 2 more than 1? It's 3. Again, it's 0, 0, so the y value, we're increasing by 1. Now that 0 turns into a 1. And again, the reference point 2, it was originally 1, 1. We already increased the x value by 2. We're going to increase the y value by 1, and we get the point 3, 2. So that's number 15. Number 16. This is base e, which I would have loved to do more with e. It's such an amazingly interesting number. And this one has an h value. And we didn't really work with h values in exponentials. We totally could have, but we didn't really. But that's fine, because this is asking about the asymptote, and that is the horizontal asymptote on exponential functions. And that is defined by the k value here. So that is, y equals 1, because the k value equals 1. So that's how to do number 16. Number 17, we want to solve this thing. Well, we have a power of 1/2 for the record. That is the same as a square root. And you cancel square roots with squares. So I'm going to square both sides, and I get x squared. And you know what? That's now a quadratic. And I'm going to solve this equation. You know what? It just occurred to me. Something just occurred to me that one of these answers, and I will have this on the completed answer key on the wall, one of these answers is actually wrong. I committed a sin, a mathematical sin. Anyways, let's continue. I want everything on one side so I can use one of my strategies, for instance, the quadratic formula. In this case, I chose to factor because it just so happens that this was factorable. That's one of the reasons we factored so much back in this unit. This was unit 3, I want to say, maybe 4. And that was because if you can notice that it is factorable, it's solved way, way faster. And yeah, this is factorable. 2 times -7 is -14, and 2 minus 7 is -5. And so we set both pieces equal to 0. For the record, this is called the zero product property because these are parentheses. Parentheses mean to multiply. That's what a product means. This is a product, a multiplication that equals 0. And in that case, you can take each piece and set it equal to 0 and solve individually. But this one on the left, he's an imposter, and I forgot to include that. He is an extraneous solution because if you plug in -2 to the original, you end up with, let's see, -2 times 5 is 10. -10, excuse me, plus 14 is 4, and we get the square root. Remember I said that 1/2 power is the same as square root. So we get the square root of 4 equals -2, and that might sound reasonable, except we define the square root function as positive only. And so x equals -2 is actually extraneous and should not be included, and I forgot about that. And I apologize sincerely. Okay, so that is, I think, where I'll call part 1, and I'll see you again in part 2.